Our discussion of polynomials leads us into something called the remainder theorem. What the remainder theorem tells us is if you divide by x minus c, then the remainder is the value of f of c, the same as if you plug the number in for x with the number c. So that's pretty cool and something that's a special thing about polynomial functions in particular. So for instance, if I take 2x to the third minus 11x squared plus 7x minus 5, and I want to illustrate the remainder theorem using f of 4. Okay, f of 4 in the remainder theorem basically tells me that if I divide by x minus 4, then the remainder is equal to the value of f of 4. So we're going to take this 4 and use it basically as our divisor for synthetic division. Our divisor is technically x minus 4, but as we did before, it's actually going to be a positive 4 in synthetic division. So we'll write 2, negative 11, 7, and negative 5. And if you'd like to do some practice for synthetic division, you may want to pause the video here and see what you get for the remainder. As we did before, we drop down the 2, multiply 4 times 2 to get 8, add negative 3, multiply negative 12, add negative 5, multiply negative 20, and then add those to get negative 25. This particular question, I'm not really concerned so much about the quotient, but just the remainder. Because what the remainder theorem tells me is that f of 4 is equal to negative 25. So we don't need to plug the number in for x. Essentially, this tells me that the value for f of 4, if I plugged 4 in for x, I'd get the same thing of that I did here for the remainder, negative 25. Let's try another one here. Let's look at f of x is equal to x to the 4th minus 5x to the 3rd plus 5x squared plus 5x minus 6. We're going to calculate f of 2 to get the remainder from division here. Technically, we're dividing by x minus 2, and that's again why we're using synthetic division, is we can do that here. 2 is going to be the number we use as our divisor in synthetic division. I'm going to write down 1, negative 5, positive 5, positive 5, and negative 6 from our function up above. We'll run through the process of synthetic division to see what happens. If I bring down the 1, then multiply by 2, then add, we'll get negative 3. Multiply to get negative 6, add negative 1. Multiply by 2 would be negative 2, add together, we'll get positive 3. 2 times positive 3 is positive 6, and if we add negative and positive 6, we have 0. A 0 remainder. There's a lot of consequences from having a 0 remainder. First off, the remainder theorem again tells us that then the value of f of 2 is equal to the remainder of 0. So what does that tell us if you have a remainder of 0? Well, a lot of things. If the remainder is 0, then we say the divisor is a blank of the dividend. In other words, if you divide a number by another number, for instance, and you get a remainder of 0, for instance, 4 divides into 48 12 times with remainder of 0, we would say 4 is a blank of 48. The word we're looking for is factor. If 4 divides into 48 with a remainder of 0, then 4 is a factor of 48. The same is happening with polynomials. Up above, we got a remainder of 0. So that tells me that I have a factor of the polynomial. We can say, since we divided by, in this case, x minus 2 essentially, we say x minus 2 is a factor of f of x. if we have a remainder of 0. That gives rise to what's called the factor theorem, which basically tells us that if f of c is equal to 0, then x minus c is a factor of our function. Conversely, if x minus c is a factor, then our remainder must be equal to 0. We could even add a third thing to this. It also means c is also called a root / 0 of f of x, which is ultimately a good thing to know if we're trying to solve. And that's what we're actually going to be looking at in the next few examples. So here's an example in particular where we leverage this factor theorem. It says given x equals 2 is a 0 of f of x, find the other zeros of f of x equals 2x cubed minus 5x squared plus x plus 2. So what we do is we use the fact that x equals 2 with synthetic division to divide and factor out a factor of x minus 2 from our function 2x to the third minus 5x squared plus x plus 2. So to set up this with synthetic division, we're going to use the 2 with synthetic division, dividing into the 2, -5, 1, and 2 from our function. And so we'll set this up, we'll do the synthetic division, bring down the 2. 2 times 2 is 4. 4 plus -5 is -1. -1 times 2 is -2. Plus 1 is -1. 2 times -1 is -2. And those add together at the end to get what we would expect to be a 0. 0 remainder goes together with the fact that x equals 2 is a 0 of the function. And so now what we're trying to do is to solve for the other zeros. What we're going to do is set the quotient that we just got to 0 and solve. So our quotient with the 2, -1, -1 would go 2x squared minus x minus 1. We're setting that equal to 0. Now this is a quadratic equation at this point. There are two strategies we could have to use perhaps to try to solve this, and either that would be by factoring or by the quadratic formula. Factoring is kind of the first choice if it works, quadratic formula if we can't factor it. If you want to take a second to look at this and see if you can factor this particular quadratic equation. Indeed, it does factor. It factors to be 2x plus 1 times x minus 1. So we have those two factors. To solve, we'll set each of those factors equal to 0. So we have 2x plus 1 equal to 0 and x minus 1 equal to 0. For the first thing, I'll subtract over a 1. I have 2x equal to -1. We divide out the 2, and we have x is equal to -1 over 2. And then we add over a 1 on this other thing to get x equals 1. So now we've solved for 2 more zeros of our function. And so we altogether, we have 3 total zeros, including the one that it told us at the very beginning. It told us a 2 at the start. So we have a 2, a 1, and a -1/2 for all the x values that are zeros of our function. Now on this one it says given x equals -2 is a root of f of x, find the other zeros of f of x equals x cubed plus 2x squared plus 16x plus 32. All right, so how we're going to have to do this one, we're going to use synthetic division again. In this case, we'll be using the x equals -2 and our polynomial function x cubed plus 2x squared plus 16x plus 32. To set up the synthetic division here like we've done the last few times, we'll start with the -2, and then we'll put 1, 2, 16, 32, and run through the synthetic division process here. Feel free, if you'd like, to pause the video here if you want extra practice with synthetic division. In a second, I'll go ahead and work it through. Bring down the 1. 1 times -2 is -2, plus, with the positive, would get a 0. But then -2 times 0 is still 0, plus 16 is 16. 16 times -2 is -32. Added together, those are 0. So looking at what we just received for our quotient, we have a 1 in the front. That's for the x squared, 1x squared in other words, but we just usually write x squared. The term in the middle won't be there because it's 0, so we have just that plus 16. We continue to solve for x by setting that equal to 0. This does not immediately factor, but it is only 2 terms. We can just subtract over the 16 to get started. X squared is equal to -16. When I write it like this, to solve for x, I can take the square root of both sides with a plus or minus in front of the other square root. So that brings it down to x is equal to plus or minus square root -16. This is not a real number solution. Since though I'm dealing with just general solutions here, I'm actually going to expand the solutions to include imaginary numbers as well. If I wanted to write this as an imaginary solution, I would put an I in front of the square root and make that a positive 16. And I do know what plus or square root 16 would be. That would just be 4. So this would be plus or minus 4i. So our function has 3 zeros, the -2 that it told me at the start, and 2 additional imaginary solutions of -4i and +4i.